Yes, dear, mic was off. Thanks for yes, it is now on. So in this lecture, we will be learning band pass modulation and demodulation. Modulation meaning to change. So we change the characteristic of a sinusoidal waveform in accordance to the message signal. So that process is called modulation. And when we do that, we are actually shifting the frequency of a baseband signal to some high frequency. And we also see in this lecture how to recover to demodulate a waveform which is being received as the receiver as a modulated signal. Then we have an explanation that tells us why we need modulation, why to modulate. So most channels require the baseband signal to be shifted to a higher frequency. As we say that when we modulate, we have information signal, that is baseband signal, and we also have the band pass signal, which is a high frequency signal. So we change the characteristic of the band pass signal in accordance to the baseband signal. So that is, we are shifting the information from baseband signal to the band pass signal. For example, in case of a wireless channel, antenna size is inversely proportional to the center frequency. And this is difficult to realize for baseband signals. So baseband signals are typically frequencies in kilohertz. And if you have frequencies in kilohertz, that means the frequency is low. So that means the antenna size will be very high. So sometimes the antenna sizes are impractical, or you cannot realize such size antenna. So we need something so that we can reduce the size of antenna. One way is to do the modulation that will reduce the size of antenna. How frequency affect the antenna is shown in this example that says for a speed signal of 3 kilohertz, lambda will be equal to C over F. And if we even use monopole antenna, that we divide lambda by 4 and then it is equal to 15 miles. So that 15 miles that is will be equal to 15 into 1.6 kilometer. So that is like 24 kilometers. So 24-kilometer antenna is practically unrealizable. 24 kilometers, that means from Hyderabad to Jamshoro, that the distance of an antenna. So that size of antenna is impractical to realize. So same SP signal, if amplitude modulated using frequency 900 megahertz, will require an antenna size of about only 8 centimeters. See, so as we increase the frequency, the antenna size reduced. So 8 centimeter antenna can be realized, which is a practical antenna. So this is evident that efficient antenna of realistic physical size is needed for radio communication system, and that is only possible with modulation. Modulation also required if channel has to be shared by several transmitters, that is frequency deviant multiplexing. Then each one has to be assigned a different frequency. So digital band pass modulation techniques, three ways of representing band pass signal. So in that we also have ASK, amplitude shift keying, phase shift keying, frequency shift keying. and the quadrature amplitude modulation, that is the combination of amplitude plus phase. So as the name suggests, amplitude shifting, that means we will be shifting the information in the amplitude of the carrier, and we will be shifting phase so that we can modulate the information over the carrier, same in the frequency. So equation 1 is V of t is equal to V sine 2 pi into f of t plus theta, where you can see all these three are the four characteristics that we can vary in accordance to the message signal and superimpose that message signal over the carrier to transmit our information. So if we are changing the voltage level of the carrier signal according to the message signal, then that is called ASK. If you are changing the frequency, then FSK. If you are changing the phase, then PSK. If you are changing ASK as well as the PSK, means if you're changing the amplitude as well as the phase, then that is called quadrature amplitude modulation. So there are techniques that allow to change just one character, but also allow us to change the two characters as well. Two characteristics of the sinusoidal waveform. You can also represent the this modulated output of a digital signal through phasor, or you can also represent the sinusoid in phasor. Consider the trigonometric identity called Euler's theorem, in that we have Ej omega naught t is equal to cos omega naught t plus j sin omega naught t. Euler's theorem, you might have heard or learned. In that we have a real part that is cos omega naught t, and we have an imaginary part that is j sin omega naught t. So using this identity, we can have the phasor representation of the sinusoids, as you can see in the figure 4.2, where on the vertical axis we have imaginary, that is quadrature. On the x-axis, horizontal axis, we have the cos component, uh, because cos 0 is equal to 1 and cos sine 90 is equal to 1. So sine will be on the vertical axis on the quadrature, and cos will be on the x-axis. Then we have some terms. Uh, People sometimes confuse baud with the bit rate. So baud is different from the bit rate. It's a term that is often misunderstood and commonly confused with bit rate. Bit rate refers to the rate of change of a digital information signals, which is usually binary. Can be more than binary, but it is binary. It's bit rate, means how many bits we are transmitting. But baud is something like different. So if you say a layman example, can be like a motorcycle can carry two people. In worst case scenario, three people. So the motorcycle can be seen as a baud, and the people riding this motorcycle can be seen as the bit rate. So that is the difference between bit rate and baud. Baud is like a bit rate, but is also a rate of change of a signal on the transmission medium after encoding and modulation have occurred. So bit rate is bits per second, how many bits are being transmitted. So we are not concerned with the any process here, but for baud it is very important. Baud can be made after modulation. After encoding and modulation have occurred, then you can measure the baud rate. But bit rate you can calculate at any moment. It should be same even before the encoding. It should be same even after the encoding. But the baud will change, or you can measure the correct value of baud after the modulation. Hence, baud is a unit of transmission rate. modulation rate are symbol rate, and therefore the terms symbols per second and baud are often used interchangeably. So baud has many definitions. One definition is that how many symbols uh, being transmitted in 1 second. How many signaling elements are being transmitted in 1 second. So all these definitions are mathematically same. So baud is the reciprocal of the time of one output signaling element, and a signaling element may represent several information bits. So it's not necessary that baud rate and bit rate should be equal. If it is, if it is that the rate of the two is same, that means eh, eh, we are using some modulation scheme that is transmitting 1 bit per symbol. In that only case, bit rate will be equal to the baud rate. But if we are using any high order modulation scheme where we have like 4 PSK, where we are transmitting 2 bits per symbol, then the baud rate will be half of the bit rate. So baud is equal to reciprocal of the symbol rate. Whatever the symbol rate is, reciprocal of that is your baud rate, and TS is equal to time of one signaling element, and 1 over TS is the 1 over TS can be equal to RS, that is the symbol rate. How many symbols are being transmitted in 1 second? So symbol rate is equal to baud. So if you know the symbol rate, that means you know the baud rate. A signaling element is sometimes called symbol and could be encoded as a change in the amplitude, frequency, or phase. For example, binary signals are generally encoded and transmitted 1 bit at a time in the form of discrete voltage levels, representing logic ones and zeros, lows. A bar is also transmitted one at a time. However, a bar may represent more than one information bit. So thus the baud of data communication system may be considerably less than the bit rate. In binary systems such as binary FSK and binary PSK, baud and bit rate are baud and bits per second are equal. However, in higher level systems such as QPSK and 8PSK, BPS is always greater than baud. So here are some basic modulation schemes and some uh, binary modulation scheme. So generally names are amplitude shifting ASK, frequency shifting FSK, phase shifting PSK, amplitude phase king APK. So if they are binary, that is means m is equal to 2, that is 2 power n, and n is equal to 1. We have binary amplitude shifting, then binary phase shifting BPSK, and then binary phase frequency shifting, that is BFSK. For n greater than 2, many variations of the above techniques exist. Exit, exist. This is exist, not exit. Usually classified as M array modulation and R detection. So for binary, when M is equal to 2, we just say binary PSK. But if it is greater than 2, then those modulation schemes are uh, said to be in a group of M array modulation or detection schemes. So ASK is obsolete. It's not used further in the communication, so we just skip this ASK. FSK use in fewer schemes now. So let's see is what is that you might have learned in the your junior semesters. It's another relatively simple low performance type of digital modulation. Uh, is a form of constant amplitude angle modulation similar to standard frequency modulation. except the modulating signal in a binary signal that varies between two discrete voltage levels rather than a continuously changing analog waveform. So consequently, FSK is sometimes called binary FSK, and the general expression for FSK is VFSK of T, that is VC, that is the peak analog carrier voltage cos 2 pi FC. FC is your analog carrier center frequency plus V of MT and delta F. So the change in frequency is in accordance to the binary input modulating signal voltage into T. So from equation 13, it can be seen that the peak shift in the carrier frequency is proportional to the amplitude of the binary input signal V of MT, and the direction of the shift is determined by the polarity. So modulating signal is a normalized binary waveform where a logic 1 is equal to plus 1 volt and a logic 0 is equal to minus 1 volt. Thus, for a logic 1 input, V of MT is equal to 1, and equation 13 can be rewritten as C. In one case, when it is logic 1, that is plus 1, it will be FC plus delta F. So that is a positive shift in frequency. And when we have logic 0, that is input V of MT is equal to minus 1, then it is the negative shift in the carrier frequency, that is FC minus delta F. And delta F is your peak change shift in the analog carrier frequency. So carrier center frequency is shifted or deviated up and down in the frequency domain by the binary input signal as shown in figure 3. As the binary input signal changes from a logic 0 to logic 1 and vice versa, the output frequency shifts between two frequency. We call that a mark, that is a logic 1 frequency, and a space for a logic 0 frequency. The mark and space frequencies are separated from the carrier frequency by the peak frequency deviation of 2 delta F. Frequency deviation is defined as the difference between either the mark or space frequency and the center frequency, or half the difference between the mark and space frequencies. The frequency deviation is listed in figure 3 and expressed mathematically as. So delta F is the difference between the two frequencies, mark and space, and divided by 2. As you can see here, we have center frequency F of C. If we have logic 1, then it is FC plus delta F. If we have logic 0, then it is FC minus F of S. So you can calculate delta F by calculating the difference between mark and space frequency and then divided by 2. We will have delta F, that is frequency deviation. So this is how it looked like. The binary input consists on 0 and 1. Analog output, that is the modulated output, will be like 0 will be transmitted on one frequency, that is low frequency. 1 will be transmitted on high frequency, so low, high, so that is goes on until the data is being transmitted. So the bit rate and baud for this particular modulation scheme should be same. Let's see. The baud for binary FSK can also be determined by substituting n is equal to 1 in equation 11. That is baud is equal to FB by n. So n is equal to 1 here. So baud will be equal to F of B. That is the baud is equal to bit rate. FSK is the exception to the rule for digital modulation, as the minimum bandwidth is not determined from equation chain. The minimum bandwidth for FSK is given as difference between F of S minus F of B and F of M minus F of B, that is F of S minus F of M plus twice of F of B. Since f of s minus f of m equals 2 delta f, the minimum bandwidth can be approximated as 2 delta f plus f of b, where b is minimum Nyquist bandwidth, delta f is frequency deviation, and f of b is your input bit rate. Now, how closely equation 15 resembles Carson's rule for determining the approximate bandwidth for an FM wave, the only difference in the two equations is that for FSK, the bit rate is substituted for the modulating signal frequency f of m. So frequency modulation you might have learned in the communication system subject, where you will learn that how to calculate the bandwidth of the frequency modulated signal, because there it has practically infinite number of sidebands. So how many sidebands you have to consider when calculating the bandwidth. So same is here, you can apply this Carson's rule to calculate the bandwidth. This expression of equation 15 to calculate the bandwidth of FSA modulated signal. So it's a simple example given here. Determine the peak frequency deviation, minimum bandwidth, baud for a binary FSK signal with a mark frequency 49 kilohertz and a space frequency of 51 kilohertz and an input bit rate of 2 kilobits per second. So that is the solution given on the next slide. Just go through it. You can also use the Bessel function to determine the approximate bandwidth for an FSK wave, as shown in figure 5. This is your figure 5. The fastest rate of change, that is highest fundamental frequency in a non-return to zero binary signal, occurs when alternating 1 and 0 are occurring, that is a square wave. Since it takes a high and low to produce a cycle, the highest fundamental frequency present in a square wave equals the repetition rate of the square wave, with which a binary signal is equal to half the bit rate. So therefore, fundamental frequency will be equal to half of the bit rate. And the formula used for modulation index in FM is also valid for FSK. Thus, H is equal to delta F by F of A, where H is equal to your modulation index called the H factor in FSK. And the worst case modulation index deviation ratio is that which yields the widest bandwidth. The worst case or widest bandwidth occurs when both the frequency deviation and the modulating signal frequency are at the maximum values. I described earlier, the peak frequency deviation in FSK is constant and always at its maximum value, and the highest fundamental frequency is equal to half of the incoming bit rate. Thus, we can rewrite equation 17 into equation 18. You can also calculate by having the difference of 2 f of m minus f of a divided by f of b, that is equation 18. So see, you can see that this is the fundamental frequency. It is equal to half of the bit rate when we have alternating 1 and 0s in the input signal. But when we have 2 zeros and 2 ones, then the fundamental frequency will be equal to f of b by 4. So this is the worst case scenario where your fundamental frequency will increase when we have alternating 1 and 0s. And this is some better situation where we don't have the alternating ones, but we have 2 zeros and 2 ones. Then the fundamental frequency will reduce to fp by 4. This is Bessel table from where you can calculate the sidebands, number of sidebands based on the modulation index. You might have used same table in the frequency modulation when you did that. Another example, Using a Bessel table, determine the minimum bandwidth for the same FSK signal. Describe in example 1 with a mark frequency of 49 kilohertz and a space frequency of 51 kilohertz and an input bit rate of 2 kilobits per second. So I give you kind of 10 minutes to solve this example. So in 10 minutes, everybody should solve it and provide an answer to this. Okay, please solve this example. Only 9 people have answered this particular examples. That means only others are only have joined us. They are now listening. So that is the solution where h is equal 1 and bandwidth is 6,000 hertz, 6 kilohertz. That is. Then we have this FSK transmitter. Figure 6 shows a FSK transmitter, that is voltage control output VCO. In the FSK modulator we have, and the input as an NRZ binary input. So which is very similar to conventional FM modulator and is very often a voltage controlled oscillator. The center frequency is chosen such that it falls halfway between the mark and space frequencies. A logic 1 input shift the VCO output to the mark frequency, and a logic 0 input shift the VCO output to the space frequency. So that is a logic that is followed in the FSK. Consequently, as the binary input signal changes back and forth between logic 1 and 0 condition, the VCO output shifts or deviates back and forth between the mark and space frequencies. VCO FSK modulator can be operated in the sweep mode, where the peak frequency deviation is simply the product of the binary input voltage and the deviation sensitivity of the VCO. With the sweep mode of modulation, the frequency deviation is expressed mathematically as delta F is equal V of MT KT, where KT is deviation sensitivity, that is hertz per volt, and V of MT, that is the input signal, input binary modulating signal, and delta F is the peak deviation frequency. Whereas in receiver is quite simple with a circuit such as the one shown in figure 7. So this is your FSK non-coherent demodulator, and this one is coherent modulator. You can see the one need the carrier here to be multiplied with the input. So that is the for the coherent detection we need phase information, whereas non-coherent detection we don't need the carrier multiplier here, and it is the data is recovered through envelope detector and the compressor comparator, and then we have the data out where here we have the low pass filter. The FSK input signal is simultaneously applied to the into the inputs of both band pass filter through a power filter. The respective filter passes only the mark or only the space frequency onto its respective envelope detector. The envelope detector in turn indicates the total power in each passband, and the comparator responds to the largest of two powers. The type of FSK detection is referred to as non-coherent detection. There is no frequency involved in the demodulation process that is synchronized either in phase, frequency, or both with the incoming FSK signal. So this is PLL FSK demodulated phase lock loop, and there is continuous phase shifting. So normally we have the discontinuity when we move from mark frequency to space frequency. You can see the discontinuity. So there is another type of FSK that is called continuous phase frequency shifting, where you will see the absolute no change or no disruption in the phase when you move from the mark frequency to the space frequency. And then we have the PSK, that is PSK is another form of angle modulated constant amplitude digital modulation. It's an M-array digital modulation scheme. It's similar to conventional phase modulation, except with PSK, the input is a binary digital signal, and there are a limited number of output phases possible. So the input binary information is encoded into groups of bits before modulating the carrier. The number of bits in a group ranges from 1 to 12 or more. The number of output phases is defined by M as described in equation 6 and determined by the number of bits in the group, that is 2 power n is equal to M. Now in FSK, we have only binary FSK. We can have either 1, 0 or 1, and we can have two frequencies, mark and space frequencies. So, but here we are, so that is how using the frequency of the carrier, we were transmitting the our modulating signal information. But here what we are doing, we are keeping our information in the phase of the carrier. And total phase available with us is 360 degrees. That means we have limited available phase. And if we go with the M array modulation scheme, so as we go with the high order modulation scheme, the phase difference between the symbols will be keep decreasing. Like if we say we are using BPSK, so BPSK means we have possible two inputs, 0 and 1, a binary. So 360 divided by 2, that is 180. That means the two symbols are the two inputs or outputs are separated from each other by 180 degrees. So as we increase the number of outputs, that is the number of bits per symbol, the phase between the symbols will be decreasing. So PSK has a limitation over the phase. So the number of output phases is defined by M as described in equation 6 and determined by the number of bits in a group. So like if we have only one bit in a group, then n will be equal to 1, then 2 power 1 will be equal to 2. So there will be only 2 phase outputs. If n is equal to 2, that is 2 bits per group, that means 4 phases. Then 4 phases means we have to divide 360 by 4. That is how we will have the 4 phases. So the simplest form of PSK is a binary phase shifting, that is BPSK, where n is equal to 1 and m is equal to 2. Therefore, with BPSK, two phases are possible for the carrier. One phase represents a logic 1 and the other represents the logic 0. So as the input digital signal changes state, that is from a 1 to a 0 or from a 0 to a 1, the phase of the output carrier shifts between two angles that are separated by 180 degrees. Hence, other names for BPSK are phase reversal keying, biphase modulation, and it's a form of continuous wave modulation of a continuous wave signal. The figure 12 shows the BPSK transmitter. So this one is the BPSK transmitter, where you can see we have the binary data input. Then we have the level converter from unipolar to bipolar. Then we have balance modulator that takes as a sine omega CT as a reference oscillator. And then we have the band pass filter, and then we have the modulated PSK output. Depending on the logic condition of the digital input, the carrier is transferred to the output either in phase or 180 degrees out of phase with the reference carrier oscillator. Figure 13, this one is shows you the balanced ring modulator, logic 1 input and logic 0 output. You might have learned this ring modulator in the basic electronics, maybe when you have did the rectifier, bridge rectification, if I am calling it correctly. So that was the diagram of a balanced ring modulator. The balanced ring modulator has two inputs, a carrier that is in phase with the reference oscillator and a binary digital data. For the balanced modulator to operate properly, the digital input voltage must be much greater than the peak carrier voltage This ensured that the digital input controls the on-off state of the diodes D1 and D1 to D4. If binary input is a logic 1, that is positive voltage, diode D1 and D2 are forward bias and on, while diode D3 and D4 are reverse bias and off. With the polarity shown, the carrier voltage is developed across the transformer T2 in phase with the carrier voltage across T1. Consequently, the output signal is in phase with the difference oscillator. So that is the working of the this balance ring modulator. So see, when we have sin omega ct as a reference carrier input, and if we have logic 1, so this is logic 1 when we have as the input as a logic 1, that is binary 1. So that will comes as sin omega ct. If it is 0, then it comes as minus sin omega ct. So the two, one is 0 degrees and one is at the 180 degrees. So from the carrier, we will know that what is the angle that we, which angle is transmitting this, which information. So if the binary input is a logic 0, diodes D1 and D2 are reverse bias and off, while diodes D3 and D4 are forward bias. That we see in figure 30C. As a result, the carrier voltage is developed across the transformer T2 180 degrees out of phase with the carrier voltage across T1. Consequently, the output voltage is 180 degrees out of phase with the reference oscillator. Figure 14 shows the truth table phasor diagram and constellation diagram for a BPSK modulator. A constellation diagram is a one that is sometimes called a signal state space diagram. It's similar to a phasor diagram, except that the entire phasor is not shown. Like, let's see. So this is your truth table. Logic 1, 180 degrees. Logic 0, 180 degrees. Logic 1 is 0 degrees. So these are your 2 points. Logic 1, logic 0, 180 degrees, 180 degrees, sin omega ct minus sin omega ct. And that is your constellation diagram where we only show the points where the symbols will appear. One at 0 degrees for logic 1 and one is at 180 degrees at logic 0. Bandwidth considerations of BPSK. Balanced modulator is a product modulator. The output signal is the product of the two input signals. So in a BPSK modulator, the carrier input signal is multiplied by the binary data. If one voltage is assigned to a logic 1 and one voltage is assigned to a logic 0, the input carrier sin omega ct is multiplied by either plus 1 or minus 1. Consequently, the output signal is either plus sin omega ct or minus sin omega ct. The first represents a signal that is in phase and a reference oscillator. The later, a signal that is 180 degrees out of phase with the reference oscillator. Each time the input logic condition changes, the output phase changes. Consequently, for BPSK, the output rate of change, that is baud, is equal to the input rate of change, and the widest output bandwidth occurs where the input binary data are an alternating 1 and 0 sequence. In that case, the fundamental frequency will be equal to half of the bit rate. So BPSK output is the multiplication of the modulating signal and the carrier signal, that is sin 2 pi f of at into sin 2 pi f ct. So these are the half sine identities. You can replace them with the formula 1 over 2 cos 2 pi fc minus f of at minus 1 over 2 cos 2 pi fc plus f of at. So from here you can see you have fc minus f of a and fc plus f of a. The difference between high and low frequencies will be equal to your bandwidth. So from here you can calculate the Nyquist bandwidth, that will be equal to twice of f of a. And because f of a is equal to fb by 2, so where fb by 2 will be substituted by f of a, then bandwidth will be equal to the f of b, that is the bit rate. So the minimum bandwidth for BPSK is the same as the bit rate, and that is also equal to the baud. So the three quantities, bandwidth, bit rate, and baud, are equal in BPSK modulation scheme. So this is output varies in relation to the input signal. You can see phase is 0 degrees. So it's starting from 0. So then we have 0 that is minus 180. So this is like this. Then no difference 0. Then minus 180. So likewise, this goes on. Then we have example 4 that says for a BPSK modulator with a carrier frequency of 70 megahertz and an input bit rate of 10 megabits per second, determine the maximum and minimum upper and lower side frequencies, draw the output spectrum, determine the Nyquist bandwidth, and calculate the baud. So take this as an homework. Send me the solutions of this overnight. The solution is there. Then we have BPSK receiver. Figure 16 shows the block diagram of a BPSK receiver. So this one, you can see we have BPSK input, band pass filter, coherent carrier recovery. Then we have ballast modulators, multiply with the carrier sin omega CT, then low pass filter, clock recovery, and the level converter that will convert unipolar binary data, or that will convert binary to unipolar. So that is how we uh, demodulate the BPSK modulation. So we stop here. We will continue from this slide. Only 2 slides remaining in this lecture. These are of BPSK receiver. We will continue from here tomorrow, inshallah. If you have any questions, you can ask.